Shall we start? Okay, so last time went somewhat slowly, so let me remind you what happened, apart from reminding you what the mistakes in the computations were. So we're talking about differential operators, L1, which looked like the sum of ui of x for I goes from 0 to n, dx to the i's power, and L2, which had a similar shape at another degree and other coefficients here. And by reparametrizing x, and the main thing we wanted to study commuting pairs of differential operators. So we assume the commutator is 0. By reparametrizing x, we can assume that the top coefficient is a constant for one, and the top coefficient is a constant for the other. And we can also assume that the lower coefficients, the next coefficients, are 0. Okay? So let us try to look at this and see what the lowest degree interesting example could be. So if m is equal to n is equal to 1, there is not so much interesting data, because this means we're just talking about ddx and ddx. Of course, dx commutes with itself, but it's not very exciting. If you look in degree 2 and degree 1, that's also not very interesting. Degree 2 and degree 2, the degree 2 differential operator will look like essentially dx squared plus some function u0 of x. Right? That's what a general thing of this sort of degree 2 will look like. Asking that two such things commute is also not particularly interesting. I mean, it's some easy enough condition for u naught and v naught. So the lowest degree interesting example would be if the degrees are 2 and 3. Okay? And the idea was as follows. Idea, we'll have a formal parameter k, and we'll have a formal power series in this parameter psi of x and k, which is the sum of certain coefficients that I denoted psi s of k, k to the minus s. This is a convention, we go in the negative direction, e to the kx. Okay? Or I could write kx minus some x naught if you prefer. It doesn't really matter much. It's just rescaling. Okay? And we're trying to look for such eigenfunctions for L1. So we want to see whether it's possible that this is equal to k to the n times un times psi of k and x. And this coefficient is chosen in such a way that it matches the agreement that the top coefficient here is just a constant, and this constant is un, so it's a number. Okay? And the proposition were as follows. I won't repeat the proof because that was painful enough. That there exists for any x naught, there exists a unique psi x naught xk solution of this thing such that it's normalized by saying that xi naught of x is identically 1, and for any s greater than or equal to 1, the value of xi x at x naught is 0. So you just normalize it so that the expansion of this power series expansion at x naught is just 1 and a bunch of zeros. And to normalize something at other points, you fix psi naught. Okay? And the proof of this was by expansion in power series, which I botched up a bit. Maybe not a bit. But in any case, that's the proof. The next proposition, which is somehow a useful technical step, was the following, that L2 commutes with L1 if and only if, and this was misstated a bit last time, so there was an extra note here, if and only if L2 psi x naught xk is equal to psi x naught xk times a of k for any x naught. Okay, so not just at x equal to x naught, but for all x. So this is to say that this function you construct for each x naught is supposed to be also an eigenfunction of L2, and the coefficient here, which is going to depend on k, should not depend on x naught. Okay. Okay. And then what I somehow claimed last time but didn't explain was the following. I claimed that there was a certain curve that appears in the picture, and that L1 and L2 are somehow related to this curve. But let me postpone this discussion and maybe just table it completely. So there is a following important theorem here that tells you where the curve appears. And this theorem is actually due to Birchnall and Chondy. This was obtained in 1922. So a long time before all the discussion of integrable, before I think the word integrable system was coined. And the theorem as follows, is that in this setup, if L1 and L2 commute, then there exists a polynomial Q of two variables, x1, x2. I don't want to use it, just such that this polynomial Q of L1 and L2 is 0 as a differential operator. Okay? So this is to say that if a pair of differential operators of this sort commutes, they satisfy an algebraic equation. So let me prove this. So this is a curve, by the way, right? The moment you write it, it's a curve in P2. So let me give a proof. The proof is as follows. So for first, suppose psi is an eigenfunction of L1 such that, as above, I mean, with eigenvalue, with value, k to the n or whatever it was, such that psi satisfies the following property. If you take psi at x naught and k, it's 0, and any derivative of psi at x naught is 0 for any I, well, from 0 to n minus 1, where n was as a degree of this differential operator, remember. Then psi is 0. So this means I fix a k, right? So I fix a k, I fix, so I have a function of x only with non-zero eigenvalue. Okay? So I'm trying to say I have a function psi of x such that L1 psi of x is equal to some number, which traditionally will denote k to the n, times psi of x. And let's say this is non-zero. Okay? So then I claim psi is identically 0. Identically 0. Because indeed, you see, if you apply L1 to psi and evaluate this at x naught, this will be essentially un times the derivative to the nth order of psi at x naught, because all the lower order derivatives just vanish. All right? And so this will imply that the nth order derivative, and it's supposed to be equal to the value, so it's 0. So it will imply that nth order derivative of psi vanishes. And then we can proceed inductively. Okay? So that's the first observation. The second observation is here in this discussion we constructed a function psi x naught, but we can also construct psi x naught of I of x eigenfunctions of L with L1 with eigenvalue k to the n, such that the way they are normalized is as the following. If you take a derivative with respect to x of psi I x naught and evaluate it at x naught, this is going to be non-zero only if you are taking the same order derivative as that. So the psi x naught that we had before is equal to psi x naught 0. The zeroth order derivative is non-zero. Okay. How do you do this? Well, you just write this out and you solve the things term by term in the power series expansion. So again, the psi x naught had value 1 at x naught and everywhere. I mean, the lowest order term was 1. And had all the other terms 0 at x naught. Right? And now we want the one non-zero term among the first n only for any ij equal to 0 dot n minus 1. Right? So now we want to find an eigenfunction such that its derivative at x naught is non-zero, and you fix which one. And of the first n derivatives, this is only non-zero one. Okay? Then it follows then this psi naught x naught dot psi whatever the thing was, n minus 1 x naught of x form a basis of the eigenspace of L1 with eigenvalue. Well, let's introduce notation E for k to the n times un. I was forgetting un here. Okay. So in that, so this is because they're certainly in there, and if you take any element of this eigenspace, you subtract a suitable combination of these to kill off the first n derivatives, it has to be 0. Okay, so this is a non-dimensional space. The fact they are linearly independent is obvious because their different derivatives are different. Okay, so then the action of L2 on this eigenspace, and it is given by a certain matrix. Okay, and this matrix is going to depend on E, this thing, polynomially. Just work it out from everything that happened here. So thus, this matrix has a characteristic polynomial Q. Well, it's a polynomial, it's Q of x with coefficients being polynomials in E. So we can consider it as a polynomial Q of x and E. Okay? So it's degree n polynomial in x and degree sumption polynomial in E. We cannot so easily compute the degree of this polynomial in E. Okay? So finally, I want to claim that Q of L1 and L2 is equal to 0. Okay? So here is a proof of this statement. So the method is going to be very simple. I'll just evaluate this thing it's a differential operator. I'll evaluate it at psi x naught I corresponding to some e, right? And this is 0 by definition, because this is a characteristic polynomial, and the action, so it means its action on this eigenspace is 0. And this has to be true for any e. So thus, Q of L1, L2 has an infinite dimensional kernel, because we can vary the e, but thus it's 0, because this is a differential operator in one variable. It can only have a finite dimensional kernel. It can't have an infinite dimensional kernel. So that's the end of the proof of this theorem. Okay. There are a couple of computations involved here. You need to make sure that such things exist, so you do it term by term. You need to convince yourselves that the coefficients of L2 in fact will be polynomial. You just write down with this what all of this means, and that's it. Okay. So this is how you get a curve. Okay. And then there was a certain theorem I stated last time, is that which was that if you have L1 and L2, their common eigenfunctions are somehow parametrized by a curve. I won't restate the theorem. I stated it, I think I wrote zeros instead of poles in one place, but let's not worry about it too much, because I want it now to go in the opposite direction. So this tells you where you would expect to get a curve from a pair of commuting differential operators. On the other hand, you can ask, given a curve, where do you see the commuting differential operators? So let's do that. So
by the way, the qx in x, x in qx is not the same as...
oh, sorry. I mean, it's, I don't know. Maybe I should write lambda. So this is I mean, it's an n by n matrix which has a characteristic polynomial. So that's the determinant of, you know, lambda times identity minus this matrix. Sorry, this was not the same x. Yeah. There are too many x's, I agree. Okay. So now what I want to do is, so this was, you know, a pair of commuting differential operators. We got a curve. Okay. So here is a curve, and then there is a discussion that I don't want to prove that actually this curve will parameterize the space of solutions. It's needed, but I won't do it. I also wanted to remark one other thing. So suppose you have such a pair, L1 and L2. You can ask, well, suppose I keep L1 the same and I change L2 to another differential operator commuting with L1. What will change? It turns out that if you have another operator commuting with L1, it will also commute with L2, and there is an entire ring of commuting differential operators for which you have the same curve, which is called the spectral curve. But unfortunately, I don't have a chance to discuss this now. Okay. So now what I want to discuss is from a curve, I'll get some psi, and then I'll get differential operators. Okay. This is the direction I'd like to go in now. Okay. There is one fact we have not discussed before, and I'll just need to mention it here without a proof, unfortunately. So this is still part of Riemann's Theta Singularity Serum. The fact is as follows. For any divisor D equal to P1 plus ... Pg, so this is an effective divisor on a curve of genus G, the theta function of P of the Abel-Jacobi image of P minus D minus R, where the Abel-Jacobi map is a map that sends the curve into its Jacobian, and R is Riemann's constant. Either vanishes identically as a function of the point on the curve if the divisor d is special. So this is to say that if h naught of d does not have the expected dimension 1 but has higher dimension. Or has g zeros at p1 ... pg. The points pi are allowed to coincide, doesn't matter, as long as they're not. This is still true. Okay, I won't have a chance to prove this, but let's assume this because I'll need this for the construction. Okay. Why do I care about this? Is because this allows, so remember when we started discussing the analytic theory of theta functions, we discussed how we construct functions on elliptic curves. And then I was able to control where the theta function has zeros on an elliptic curve. And then I said that there is a similar procedure in general for a curve of higher genus, but on a curve of higher genus, a theta function generically has g zeros if you shift it. And this is how you control where the zeros are. So this is a similar statement. It's harder, of course. I mean, you need to prove it. Okay. So the following definition, so the names of Zakharov and Shabbat should be mentioned here. The names of Baker and Ahiezer should be mentioned. And the name of Krichever should be mentioned. But the common terminology now is the following, that a function psi is called a function, psi of x and p, function, no, just of p, is called a Baker Ahiezer function on a curve C for the set of data consisting of the following: a point P naught in C, a divisor D not containing P naught generic, on C, a polynomial Q in one variable, and I'll call the variable K, which should remind you of the K we had before, if the following holds: if 1, psi is meromorphic on the curve C without the point P naught, with poles at the divisor D only. Okay. So this means that everywhere except one point, the function psi is meromorphic. At this one point, I haven't said anything yet. And it's only allowed to have poles at this divisor D that we chose. Everywhere else it's holomorphic. And second is for a local coordinate, so there is also a data, a local coordinate Z, which is K inverse near P naught. So this is what makes the situation much worse, because this is an infinite set of data. A local coordinate is it's a jet, it's an infinite Taylor series at a point. So this is infinitely much data, this is finitely much data. Okay? So for a local coordinate, Z is equal to K inverse near P naught. What does this mean? So what I mean is that Z of P naught is 0 and K of P naught is infinity. the function psi of p times the exponent of q of k is holomorphic near p naught and has value 1 at p naught. So what does this condition really mean? So this is something very strange. So let me remind you. So k goes to infinity. E to the minus q of k. To make notations more consistent. Okay. And what happens? So this sort of goes to infinity. Let's not worry too much about k, plus minus. So k goes to infinity near p naught. So what this means is that I am allowing the function psi to have an essential singularity at the point p naught, which will locally look like e to the q of k. So it will locally look like e to the 1 over z plus some coefficient a times 1 over z plus some coefficient a2 times 1 over z squared plus and so on, corresponding to the polynomial q. So this is an essential singularity of a bad kind, and it's exponential, and we don't know how to deal with it, right? So this is the kind of singularity we allow, and then there is a certain normalization which says that once you kill this singularity, the value you get is just 1. You could avoid normalizing, but it's more convenient for me to define it this way. So this is a definition, right? I mean, I can define anything I like. Now I'll need to prove something useful about this object. And the useful thing will be the following theorem, due to Ahiezer. And somewhat more generalized, in fact. This theorem is as follows. For D and Q generic, and I won't specify exactly what generic means, but for an open set of D and an open set of Q, there exists a unique Baker-Ahiezer function psi on the curve C. Okay. So let's give a proof. So uniqueness. So suppose psi1 and psi2 were two different such functions. Then if you take psi1 and divide it by psi2, right, this is going to be meromorphic now on C, because the essential singularity is exactly the same. We just cancelled it precisely. And moreover, psi1 over psi2 at the point p naught is going to be equal to 1 because of our normalization. Where is this going to have zeros? Well, in poles, so whatever poles we had at the divisor D will cancel. If you compute the degree, you will see that there are g other zeros floating around. So has g zeros at a non-special generically. Zeros and poles at a generically non-special divisor, which is impossible. So that's uniqueness. So uniqueness is sort of automatic. I mean, as long as I don't worry about what exactly I mean by non-special, it's safe. If you don't like this so much, I mean, I'll write a precise formula for psi 1. So I'll write one solution, then you'll see that its zeros are sufficiently generic. This will work immediately. Okay. Existence is going to be by construction. So I'll explicitly construct such a function. Okay. So remark that if you were to take a theta function of tau and z, and if you were to add to it n tau plus m to the argument z, right? So I'm going to write a formula now which will be written on c to the g, but will descend nicely to the abelian variety. So for this I'll need to remind you, or more precisely to tell you, what is the transformation formula for the theta function. So the theta function is a function defined on c to the g, but descends to a line bundle on the abelian variety, so I'll need to tell you what the exponent is. So what happens is that it doesn't depend on m, so it's invariant if you shift by integers. And here there is an exponent which I may not remember rightly. I have it written somewhere, but it's not very important for us. As long as you know roughly exponent, and there is always a pi I. Okay. Something like that. And you can easily verify this formula if you know what you're looking at. So you just look at the Fourier series expansion and you just shift the index by n, and this works out well. Okay. So there is a formula of this sort which will be useful. So now what I want to do is I want to construct such a function. So what does this mean? I need to construct something that will have prescribed poles and zeros somewhere. Well, to have prescribed poles as a divisor d, I can use this thing. This has zeros in d, so if I take 1 over that, I will certainly get a function that will be 0, or that will have poles precisely at d. So that part I have, right? So this means, so for psi, so let's try construct some psi. So one thing I sort of know, I would like to have theta of p. So p is a point, so this means the Abel-Jacobi image of p, but I cannot keep writing this because it will get out of hand, minus d minus r. So I want this in the denominator, because if I have this in the denominator, this thing will have g zeros precisely at d, so the 1 over it will have poles precisely at d. Okay. Of course, this is a section of a certain line bundle, so I'll need to worry to cancel it. And still, I didn't get the most important thing. I didn't get my essential singularity. So how do I get an essential singularity? Well, here is the following lemma. There exists a unique meromorphic differential omega on C with only one pole at P node, and the singular part at P node being dq of k. D means differential with respect to k. Okay? So this is to say it didn't matter what this was. So essentially I'm saying that whatever singular part you write down, there will exist a unique differential with this singular part. You might worry that maybe it will have a residue and that it cannot have a residue at a single point, but I'm writing this as a differential, as a derivative of a polynomial, so it cannot have a residue. There cannot be a term which is k inverse in such a derivative, which is k in such a derivative, sorry. Okay, so and such that its integrals, the integrals of this differential omega, are 0 over all A cycles, where A1 AG, BG1 BG is a standard basis for homology. So what does this mean? It means that if I were to take the surface, I could cut it up and I could get a polygon. Well, this is an example for genus equal to 2, and this will be A1, B1, A1, B1, A1, A2, B2, A2, B2, right? So if you were to look on a torus, this basis is this loop and such a loop. So technically, the intersection numbers of A's are equal to the intersection numbers of B's, 0, and the intersection numbers of A and B's are non-zero only for the same ones. And I mean, you just cut up every sort of handle essentially. And this is what we use to construct the Jacobian analytically anyway. So that's where it comes from. And the reason I want the A periods to be 0 is because of this essentially, that the theta function doesn't change if you go around the A period. So this is a technical condition. So let me prove this lemma. It's not so hard. Well, proof. So there certainly exists, choose a differential, I don't know, capital omega with singular part dq of k dk and the arbitrary periods. So this is existence. Okay, this is certainly possible because there exists a differential by, I don't know, writing down Laurent series or whatever you wish, or computing H naught with any singular part you'd like, right? As long as there is no residue, the only condition for a differential with prescribed singular parts to exist is that the sum of the residues is 0. We don't have any residues, so the thing exists. Then we can just let omega 1, omega j be the basis of holomorphic differentials dual to A1 through AG, which is to say that the integral of H1 is equal to delta Ij. Okay? And now we let omega to be equal to the capital omega minus the sum of these guys, chosen in such a way that we just kill the coefficients. So we take the integral of capital omega over AI. Right? The sum goes from 1 to g. If you do it this way, then obviously if you integrate omega somewhere on an A cycle, you'll get an integral of capital omega on this A cycle minus the corresponding integral from here, so it will work. So this is an existence. So let me prove uniqueness. So this is still within the lemma. Okay. So I want to show there is a unique such meromorphic differential. Okay. So if omega 1 and omega 2 were two such ones, then of course omega 1 minus omega 2 would be holomorphic. With all A periods 0. Which is impossible because these guys are a basis. So if you have a holomorphic differential with all periods one form, a holomorphic one form with all A periods 0, then it has to be a 0 linear combination of these guys. So this means omega 1 minus omega 2 is 0. So we proved the lemma.
Is it the QK the polynomial of K or
Yes,
polynomial of 1 over K?
it's a polynomial of k.
Okay.
And it's important that, I mean, it has positive powers of k. So we're going to allow a singularity, not disallow it. So I'm erasing the definition of the Baker-Archiesa function now, but you remember that all what I need to do is I need to construct an essential singularity. Okay? So what I'm going to do is the following. I'm just going to write down a formula. So psi of p I'm going to define in the following way. It's going to be the integral from p naught to p of omega, right, where this omega is that omega, times the theta function. So down below it should be the theta function of p minus d minus r. Up above I would like to write something very much similar, so I would still like to write p minus d minus r to cancel the ambiguity, because this is only well defined on c to the g. But I also have some ambiguity from here, so I'll have to add u, where u is the vector of b periods of omega. So this is to say u is equal to, you know, the integral of omega over b1, the integral of omega over bg. Let's check. Yes. Okay. So now you notice that it's explicitly written, so you know where the zeros are. Sorry, there is a the exponential of this thing. Okay. So that's the definition of this function, and I would like to claim that psi of p has the correct kind of singularity, because this thing has the singularity of the kind dq. So this means when I integrate it will have singularity q, and this will have singularity e to the q. So that's good. Psi p I would like to claim is well defined as a function on the Riemann surface and not as a function on the universal cover. For that you need to check that if you take a point P and you add a period vector to it, then in fact this doesn't change psi, because this is technically written on the Jacobian, and not even on the Jacobian, but on c to the g. Okay? And thirdly, I cannot claim that psi of p naught is what it is, so we need to consider psi of p times a constant, so that the normalization at p naught is correct. And this constant can be chosen uniquely because we just look at this, look at the coefficient of the exponent, plug in p naught, we get some value, so we just divide it. So essentially what I need to divide is I just need to take theta of p naught minus d minus r divided by theta of u plus p naught minus d minus r. And then I'll be in good shape. Right, because then after removing the exponents, the value at p naught is 1. Okay. So this is a proof that there exists a unique Baker-Hiesa function for a generic divisor. So this is a construction that works as long as this is not identical to 0, right? And this means for a generic divisor T. Okay, questions?
So are you assuming the path of the exponential? Are you specifying some path in exponential in that integral?
Right, so yes, I am. So I'm doing this implicitly. So here when I'm writing theta function, I have to choose a lifting to c to the g. The lifting I choose here and the lifting of the path I choose here should be the same lifting. Okay. And then the claim here is that this is independent of the choice. So you can lift p one way and lift the path the same way, and then you can add to both of them some element here. And because I'm writing u here, and this is the periods of this guy, maybe it should be a minus u. Minus. Sorry. And then I think it's okay. Okay, that this will, the dependence on the choice of the path and the lifting of the point p will cancel. Okay, so this is a general construction. Okay, now let's do the simplest example. So this is in fact the simplest non-trivial example. So let's choose q of k of degree 3. You can ask why not degree 1 and not degree 2, but the degree 3 seems to give the very interesting picture. So this means q of k is going to be equal to x times k plus y times k squared plus t times k cubed. I'm not writing the constant term because writing the constant term for the polynomial q is boring. It just means you rescale the whole thing. So there is no need to. And I just call x, y, and t as 3 coefficients, right? And the function psi, if you think about it, I mean, it depends on k, right? So the function psi is actually a function that depends on c, p1, pg, p naught, k, right? And then it's a function of p. Okay. So let me fix all of this data and let me write this as a function of p and k. And then q. Okay. So for everything fixed, you just vary k. So k is a local coordinate. You can choose a different local coordinate. Okay. So now this hopefully starts to look a little bit like what we had before. Okay. So this is my choice of a polynomial q. And here is a theorem, which is the following. There exists unique L1 differential operator in X of order 2, L2 a differential operator in X of order 3, such that L1 psi is equal d psi dy, and L2 psi is equal to d psi dt, where psi is this psi. So there is k, x, y, t here. If I'm not, and there is c, p naught, p1, pg. Right, so this depends on the polynomial, and now I want to emphasize also the dependence on which polynomial I choose. So x, y, and t are the parameters which I can choose generically. Okay. Okay. Why on earth am I writing something like that? How do you know that something like that will happen? Well, you see, there's a function psi, right? And there are x, y, and t. So what is the derivative of psi with respect to y? It just means you're sort of picking out the k cubed term, the k squared term, and for derivative with respect to t, you're picking up the k cubed term. So you would expect that some relation of this sort will happen. So let me give a proof. So, I mean, let's prove this one. The other one is the same. Okay? So, we write formally psi of x, y, t, k, p as the sum of psi s of x, y, t, p, k minus s times the exponent of the appropriate kind. Okay. The same as we did before when we were looking at the picture from the other viewpoint. We just expand this psi in formal power series in k. Okay. Now the exponent is the exponent of q of k, right? Because this is a singularity. So the singularity is supposed to be the exponent of q of k. So locally, s starts from 0, so this is an s, minus s. So you see this function psi near the point p is supposed to have the singularity of the type the exponent of q of k, so here it is, and the rest is supposed to be locally holomorphic. So that's what I'm going to write. So that's exactly what I write here. Somehow, in some sense, you shouldn't write the p anymore, right? So the k is the local coordinate of the point p if you're writing this way. Okay. So if I write it formally this way, then I claim that there exists unique L1 of order 2, and in fact, you can compute that L1 is just going to be d squared over dx squared plus some u of x. I'll tell you what u of x is in a second. Such that L1 minus d dy applied to psi is equal to the exponent of q of k times O capital of k inverse. Okay, so that there is no constant term. Right? So how do you see that? That I won't do. So to see this, you formally solve for the coefficients of L1 term by term. So you see, if you take this psi and you differentiate with respect to y, you are picking up a coefficient of k squared. So if you differentiate here with respect to y, from here you are picking up a k squared. So the highest order term, if you differentiate with respect to y, there will be a derivative here. So what I'm trying to say is the following, that d dy of psi x t y k starts with k squared term plus and so on, with some coefficient, times the exponent of q of k. Right? Because the highest order term you can get, so k squared, the next one will be k plus and so on. Because here we go up, or we start with k to the zeros, but when we differentiate q of k with respect to y, this means differentiating this with respect to y, so we pick up a k squared. Okay? And we just want to cancel the first three terms. Okay, and I claim that this with u equal to minus 2 dx of psi 1 is going to work. Okay, so u of x, y, t, x, y, t. Okay, right? So I just claim that if you plug in L1 equal to d dx squared plus u of x, where u is of that form, then the first three terms will vanish. And the reason I got this formula was that supposedly or more precisely somebody else like Grushevsky, did the correct computation, and they just made sure that in the power series you can indeed cancel the first three terms. Okay, so this is a formal thing. All you need to check is essentially this coefficient somehow independent non-trivially on the things you're trying to solve for, so that there is a solution. And the highest order term is always non-degenerate, so it's fine. Okay, so thus, what you see is that if you take this L1 minus d dy psi, has the following properties. It has the same kind of singularity as psi, right? It's meromorphic. Has poles at the same places, because I mean we're not doing anything elsewhere. But the value of psi times e to the minus q of x, q of k, sorry, at p naught is 0. Right, because I killed this coefficient in the expansion. Yeah. So please change. Excuse me? How do we know? Oh, maybe we do. I'm not claiming we cannot. But you see, when we were trying to solve that, we were trying to choose the coefficients of L1. So L1 was a differential operator of degree 2. So it has the second, first, and zeroth coefficient. Somehow everything here is normalized in such a lucky way that the highest coefficient will be constant, the next coefficient will be 1, and then the next one we have to solve for. But I'm canceling the first three terms of dy by choosing L1 appropriately. Does this make sense? So I'm trying to solve this, so I want this to be equal to O of k inverse, right, times the exponent of q of k, right? That's what I'm trying to achieve, right? And I'm claiming that a solution has the form L1 like that. So anyway, so this thing now has the same kind of essential singularity as psi does. It has poles at the same places, and the values of it at p naught is 0. If that is the case, thus I want to claim that L1 minus d dy psi is 0. Not to any order, but just 0. Because it's a function on the Riemann surface which satisfies all the same conditions as the Baker-Archieder function, except it's normalized to be 0. The space of Baker-Archieder functions is, there is a unique such normalized to be 1. So if you had such a function, you would be able to add it to the Baker-Archieder function and get another one. So that's impossible. So by the uniqueness of the Baker-Archieder function. Okay. Well, I think I have another 2 minutes, so I wanted to wrap this up to somewhere. Yeah, and the proof that you can find an operator L2 that will satisfy this is the same. A simple corollary of this is the following, that L1 minus d dy and L2 minus d dt commute, because they have so proof psi of k for any k is their common eigenfunction. Right? And so this means, so this vanishes on any psi of k, but this is an infinite dimensional space of functions again, so and this operator, and since the commutator is a differential operator in x only, so you see there are y and t appearing, and for differential operators in many variables we don't know anything. But if you commute, all you're doing is you're taking the derivative of this respect to y and derivative of this respect to t. You're no longer left with any differentiation with respect to y and t. So this means this thing has a finite kernel. And so it has to be 0 because it has an infinite dimensional space of solutions. Okay. And now if you write this out, so writing out the commutator, writing out u in terms of theta, right? Because in terms of psi, and thus in terms of theta, because u, remember, was this thing, right? Gives us a relation, gives an equation, PD for u. So u, remember, was this coefficient of L1. So L1 was d squared dx squared plus u of x. L2 had the highest order term, so L2 actually had the form d cube x plus 3/2 u dx plus some w. And you can, and from this equation you can express w in terms of u, but something will be left. So the equation you'll get for u will be u y. And this is the KP equation. That's why I wanted to write it down. Well, anyway, I think I know what it is. So it's the same as dx of ut minus ux 3/2 plus uxxx over 4. For u being equal to minus 2 d squared x log of theta of ux plus vy plus wz plus wt plus z. Okay, where z is a point on c to the g, x, y, t are our parameters, and u, v, w are, let me say what they are, let me write it here. So u, v, w are the b periods of the meromorphic differentials with singular parts 1 over z, dz over z squared, dz over z cubed, dz over z fourth at p naught. Okay. Which is actually the same as the derivative of the canonical map that we discussed before. Okay. So this is how you get the KP equation starting from an algebraic curve. So you have a curve, the curve with a bunch of extra data, with an infinite dimensional bunch of extra data, defines for you a Baker-Hieser function. This Baker-Hieser function is as a common eigenfunction of the common kernel of two operators, L1 minus ddy and L2 minus ddt. Then these operators commute. This means that their coefficient satisfies an identity. When you rewrite it all through, when you write that, u is equal to the derivative of the first coefficient of the expansion of the Baker-Hieser function, the Baker-Hieser function is a certain expression involving the exponent of a differential, the integral of a differential and theta function, you eventually get an identity for theta functions, and this is the identity you get. Why this is the identity you get? Well, you just sit down and compute, and after a couple of pages, that's the answer, right? This is the KP equation. Okay, so let me stop here. In the next hour, I'll finally tell you something about how you show that this consideration characterizes Jacobians. Thank you.